Now that we have defined all the ray tracing inputs for DTRM, the next step is to create the ray file. This is used during the actual radiation calculations. The file contains ray traces in the form of path lengths and data of cells traversed by each ray. Now this ray file is dependent on the boundary conditions, mesh and radiation model inputs. Hence, if you change any of these, you have to recreate the ray file. You can open the DTRM ray dialog box directly with the define DTRM rays menu item. So we have to change the type of boundary condition. If we change the type of boundary condition, adapt or reorder the mesh or scale the mesh, we have to rewrite the ray file. We can also see the cluster and DTRM rays by clicking on the display cluster button in the DTRM rays dialog box. So if we click on display, we can see the clusters as well as the rays that are created for solving DTRM. After DTRM, we will see the H2S model. The name of the model is surface to surface model. The model is for non-participating media only, hence only surface radiate or take part in the radiation. The method is based on view factor calculation principle of Chaparral. Depending on the number of surfaces taking part in the radiation, a n by n matrix solver solves the radiation calculations using the view factors for each surface. So this is a sort of a radiation calculation based on surface view factors. For calculating view factors, a matrix n by n matrix is solved, which is based on the Chaparral view factor calculations. J is the radiosity vector here, and E is the emissive power vector. K is the n by n matrix that we need for calculating view factors. View factors is defined by this particular integral. We have seen the concept or input of surface cluster once in the DTRM model. This concept is also required in the H2S model. What is surface clustering concept? To reduce the calculation efforts for radiation solver, the number of surfaces is reduced by creating surface clusters. The method of creating surface clusters is to start from a face and go on adding its neighbors until a specified number of faces per surface clusters is collected. What are the advantages of the H2S model? The basic principle of this model is the view factor calculation that is done once. Hence later on, it's just a matter of matrix solving, so time per iteration for this model is less. Unlike the DTRM, this model also works in parallel solver. This model also remains accurate even when the source or sink terms come in play, unlike the DO or ray tracing method. Also, since the calculations are less, it requires much smaller memory and file storage. There are also disadvantages of this model. The H2S model assumes that all surfaces are diffuse. The implementation assumes gray radiation. Storage and memory requirements increase very rapidly as the number of surfaces for view factor calculation increase. Cannot be used to model participating radiation problems. This is the biggest disadvantage of this model. Cannot be used with periodic boundary conditions. Hemicube view factor method cannot be used with symmetry boundary condition. It does not support non-conformal interfaces, hanging nodes or mesh adaptation. Now we will see how to set up this particular H2S model. First we go to the radiation model dialog box. We select the H2S model, that is here. We set the solution parameters. So we can set the solution parameters here. The view factor and clustering settings, we can go here and set up the H2S model. Here we have two options: newly compute the view factor or import previously calculated view factors. First, for H2S model, we have to know the view factors. Then we decide the view factor and clustering settings. This defines how the surface clusters are formed and how the view factors are calculated for the H2S model. Next we click on settings. That is, we click here. In this dialog box, we can specify faces per surface cluster value. This number controls the number of radiating surfaces. So surface maximum faces per surface cluster is set here. There are two options to set the faces per surface cluster value, manual or automatic. For manual, we need to set an FPSC value, which is faces per surface cluster value, for all flow boundaries in the faces per surface cluster for flow boundary zones number entry box in the manual group box. This will apply to all walls. We also need to apply this value to all wall zones that are adjacent to the fluid zones, as well as for a wall that requires a different FPSC value, we need to open the boundary condition dialog box. So if we individually have to go and set up the FPSC value, we have to go to the boundary condition dialog box and set it in the radiations tab for the H2S model. Whether we set the FPSC value manually or automatically, we have the option of modifying the cutoff or split angle between adjacent face normals for the purpose of controlling surface clustering. The split angle sets the limit for which adjacent faces are clustered. A smaller split angle allows for a better representation of the view factor. By default, no surface cluster will contain any face that has a face normal greater than 20 degrees. To modify the value of this parameter, we have to use the split angle text command. This text command is define models radiation H2S parameters split angle or file right surface clusters split angle. For calculating the view factor, there are two base options. One is face to face, which uses the boundary faces of the mesh, and other is cluster to cluster, which uses the cluster formed by settings in the cluster group box. As the number of clusters is less than the number of all faces, the cluster to cluster method is faster and computationally less expensive. These are basis options or basic options, and there are further two methods after this. When we calculate view factor, the calculations can be made using two methods. First is the ray tracing method that is available only when face to face option is selected. This is not applicable for periodic zones. The next is the hemicube method. This is available for 3D and axisymmetric cases.